My name is Paul Campanello. I'm the VP of Marketing here at Zadita. I am super excited to welcome you all to Zadita Transform 2023. I'm so happy to be able to kick off this year's Transform. For those of you not familiar with the program, for our first-time people, Transform has become the industry's premier edge computing conference. We're so fortunate because it brings together industry visionaries and experts and thought leaders, as well as practical customer examples of real live edge deployments. Transform in its third year delivers real value to customers, partners, and prospects, giving them the ability to optimize their edge initiatives. Additionally, all of our attendees will have the ability to win a raffle during the day. We have an iPad Pro at the end of the day and an Apple Watch. We have a variety of sessions set for you today. And at this point, I am thrilled to introduce our CEO and founder, Syed Ouissal. Syed?
Thank you so much, Paul. I am super thrilled to kick off the third edition of Zadita Transform. We have an incredible agenda lined up, and I can't wait to get started. But before we get started, I wanted to first take the opportunity and thank our sponsors who made today's event possible. In particular, I want to thank VMware and Emerson for their platinum sponsorship, as well as all the other sponsors for being part of this event. You will hear from many of them later today. You will also hear from two great keynote speakers we have lined up. Dr. Satya is with Carnegie Mellon and is widely considered as the father of modern edge computing. Kelsey Hightower is a distinguished engineer at Google Cloud and has been involved with cloud computing since the early days. We could not have asked for a better combination of speakers between edge and cloud as part of today's event. Let's take a quick look at the rest of the agenda. As we kick off the general session, after my introduction, we'll head straight into Dr. Satya's keynote. After Dr. Satya, we'll discuss the pitfalls of edge security. Then we will have Nathan Pettis at Emerson provide us Emerson's perspectives on edge computing. From there, we'll split the event into two more tracks, a business track and a technical track. During the business track, we'll discuss the trends and challenges of industrial IoT, as well as how to bridge the IT-OT gap. In the technical track, we'll have sessions on digital twin and how to automate the edge with APIs. After these sessions, we'll get back together for Kelsey Hightower's keynote. Then we split up again into an afternoon business and technical track. In the business track, we'll cover lessons from real edge deployments and the edge investment landscape. And in the technical track, we'll discuss if the edge requires the cloud and what the role of open source is in edge computing. Finally, we'll get together again for our closing keynote with VMware, where Sanjay Uppal from VMware and I will close out Zadita Transform. As you can see, we have a great day of content ahead of us. But first, I would like to take the opportunity to discuss the state of edge computing with all of you. Since our last Zadita Transform event, a lot has happened on the edge. But if anything is clear, it is that our initial vision of edge computing and its drivers are more evident than ever before. You see, when we founded Zadita 6 years ago to enable edge computing, we got there by understanding the relationship between two trends, IoT and cloud. IoT meaning anything that can get connected will get connected. While this started with consumers first, now industrial and enterprises have also been heavily adopting IoT to extract data from their assets, machines, and vehicles, etc. At the same time, with cloud, any application that can run in the cloud will run in the cloud. Not only because of the consumption model of the cloud, but more increasingly because it's just simpler and easier to build, develop, and run apps in the cloud than anywhere else. However, what we saw 6 years ago is that as a lot of data is coming online from these IoT devices, it would be impossible to upload all that data to the cloud. Yet the data still needs to be analyzed. So instead of trying to get the data to the cloud is being pushed to all the way to the edge of the network. And this is what we define as edge computing. We also understood that the edge would not be a single layer of place in the network. Instead, it's a tier of layers. If you visualize the cloud being at the top and the people and things at the edge, at the furthest location from the cloud at the edge, basically, as the cloud experience is pushed to the edge, it goes from highly centralized clouds and cloud-native data centers to regional and local data centers. In those cases, while the location of computing is different, the environment this computing is happening in is still pretty much the same. We still have standard racked servers in controlled physical environments with power, cooling, and physical security, and some staff on site. Solutions that enable cloud computing infrastructure will still work here, And as a matter of fact, many cloud providers offer solutions today to deploy their cloud stacks on-prem. However, what we saw when we founded Zedita is that there are further, deeper layers of edge computing that would be required. These layers of edge computing look nothing like the prior ones. Edge apps here have to be deployed on non-typical server hardware. They need to run on small form factors like industrial servers and gateways and even embedded devices. They are not in secure environments or on secure networks. They could run in other people's networks and environments. The networks could be wide area networks with intermittent connectivity and various degrees of latency like 4G, 5G, and satellite, for instance. And these apps become a lot more specific to the people and in particular the things they are serving. And last but not least, one thing is clear is that the number of locations or nodes here could be tens of thousands or even millions. So imagine machines, vehicles, production lines, well sites, substations, each enabled with edge computing. We call this type of edge the distributed edge at Zedita. This is the edge that we think is now the fastest growing in the market and entering mass deployment with many enterprises globally. In addition to the scale, the architecture of the distributed edge matters a lot. There are many elements that need to come together to architect the proper edge computing stack. For instance, you need to think about what silicon to use. You need to think about what hardware to use, what edge application frameworks, which industrial connectivity to apply, what networking to be used between edge or to the cloud, what DevOps capabilities for the cloud native services, what security profile and security capabilities to implement, what analytics, data pipeline and data management capabilities to implement. And finally, you're sending data to a cloud and you're going to need probably system integrators to help you pull all of this together. Many of these elements are third party, meaning they will not be developed by our customers themselves and they will need other vendors and other parties to help them put this together. And therefore, an ecosystem approach is needed. We saw this at Zedita very, very early on. This is not a single vendor world, and it requires an open edge architecture to be successful. And this open edge architecture using all these ecosystems requires a way to orchestrate and manage it. And this is exactly what we do. We provide edge orchestration and management to anyone looking to deploy distributed edge computing. Our solution was purpose-built for the distributed edge. It was built using an open architecture. It leverages open source. And it was built to support multiple diverse hardware, support different operating systems, provide remote management and visibility, enable customers to deploy apps and manage them anywhere, provide real-time operational insights on these apps, these devices, the networks, etc., and then ultimately network and connect all of these together and provide a very strong zero trust security framework. This is what we do. Fast forward, and since we launched our product commercially a few years back, we have learned a lot. We have learned that the edge landscape is very, very broad. It sits at the intersection of IT and OT. It is deployed in highly distributed verticals like oil and gas, renewable energy, automotive, retail, building management, and in discrete and process manufacturing. Today, Zedita has several customers in each of these verticals. We are deployed by some of the largest companies in the world in the heart of their distributed operations. We work directly with these customers on their edge computing needs from architecture to operations. We also have amazing partners such as Rockwell, Emerson, and VMware, where we have built joint solutions targeting specific use cases and verticals for their customers. I could not be more proud and excited about our progress today, and would like to thank all of our customers and partners for their trust in us. Now on to a few exciting announcements I'd like to make as part of this year's Zedita Transform Edition. First off, let's talk about Kubernetes. As many of you know, Kubernetes is the predominant cloud-native orchestration system in the world. Many who are building cloud-native software are using Kubernetes to deploy these apps in the cloud or data center. As I mentioned earlier, edge computing is all about extending the cloud to the edge. So logically, customers have been looking for ways to take cloud-native apps and deploy them using Kubernetes at the edge. In 2021, we launched a partnership with our partner SUSE to make this possible using a lightweight Kubernetes implementation and some smart software and APIs. Since then, we have many customers and deployments in place using this solution at the distributed edge. Today, I'm thrilled to announce that we have been recognized by GigaOM recently as the leader in Kubernetes for edge computing. We are thrilled for this recognition. I would like to thank GigaOM and our customers for this award. This is a big deal because actually GigaOM, as they spoke with various real customers, understood and highlighted in their report that running Kubernetes at the edge has very little to do with Kubernetes itself and everything to do with how to enable Kubernetes at the edge. This was exactly our insight as we worked with our early elite customers, that the biggest challenge is how to orchestrate Kubernetes environments at the edge, how to secure them, how to manage them, how to monitor them at scale. So with that, I'm also excited to let you know that we'll be sending each one of you a free copy of this report next week, and I hope you enjoy reading it. I'm also excited to announce that we are launching today our first free self-service trial. With this, anyone can sign up, create an account on our system, and immediately try out our Edge orchestration service. We are thrilled to open up our product for everyone, and I look forward to get your feedback and work with you on your edge computing needs. Just head down to our website and click on the sign up button to get started. It's been about 1.5 years since our last transform, and we've been making tremendous progress since then. Next to receiving several awards, which we're very, very proud of, we also launched last year Edge Academy, the industry's first free online learning center for anything edge computing. If you have not had a chance to check it out, I would recommend you to take a look. It has been built for any audience ranging from professionals, business, technical, and operations audience. We also launched a new channel program where we bring in marketplace partners as part of our Edge marketplace, along with technology companies and channel partners. And finally, from a growth and funding perspective, as edge computing takes off, we have seen great revenue growth. We also closed a new round of funding last year with some incredible new and existing investors such as Emerson, Chevron, Porsche, Rockwell, EDF, Samsung, and many, many more. All in all, we could not be more pleased with our progress, and I would like to thank the Zedita team, our customers, our partners, and our investors for their support and trust in us. Finally, if you want to learn more about edge computing, please take a look at Edge Academy. If you want to collaborate and touch the code, go to the Linux Foundation LF Edge page and check out Project Eve. And of course, please reach out to us if you want to try out our product or discuss your edge computing needs. So with that, I am super excited to introduce our first keynote speaker of Zedita Transform 2023. Dr. Satya is the Carnegie Group Professor at Computer Science at Carnegie Mellon University. He's also a fellow of the ACM and the IEEE. Dr. Satya's multi-decade research career has focused on the challenge of performance, scalability, availability, and trust in information systems that reach from the cloud to the edge of the internet. In the course of this work, he has pioneered many advances in distributed systems, mobile computing, pervasive computing, and the Internet of Things. In 2009, he wrote a publication called The Case of VM-Based Cloudlets in Mobile Computing, which led to the emergence of edge computing. Because of that, we call him the father of edge computing. Dr. Satya's favorite quote is, "Working code trumps all hype," a motto that we believe very much in here at Zedita. Without further delay, please welcome Dr. Satya, who is streaming live from the Carnegie Mellon University. Dr. Satya?
Thank you very much. Can you hear me?
We can. Please go ahead.
Perfect. Let's start my screen. Thank you very much for inviting me to this very special occasion. Although you can't see it on the camera, there are actually roughly about 60 to 80 students in this classroom in front of me. We're hearing this lecture live. So it is both for your remote audience and also for my students who are here in class. Okay, so I have half an hour and I'd like to share with you some thoughts that I hope will help you make sense of the world that is emerging. Said, in his introductory remarks, put a very beautiful pyramid with the cloud at one end, the IoT devices and humans at the other end, and then a whole lot of intermediate layers. And I'm going to really build on that idea. So this complexity that you see here is today's world. There are many, many moving parts. It's not totally clear which of them are essential, what role they play. It's kind of quite complicated. And so the question that I want to ask this morning is there a way to simplify how we think about this world? Is there a way in which we can identify themes and patterns that give us both understanding, that explain why things are the way they are, and also give us predictive power to be able to say, next year or within a short time, I bet you the following is going to happen, because that lets you anticipate trends and to be prepared for them and to take better advantage of them. So one of the founders of our field, Alan Kay, almost 40 years ago, stated the best way to predict the future is to invent it. And so thinking about it that way is very helpful. Our science, as my distinguished colleague Herb Simon, who founded our department and school, once said, is a science of the artificial. We create the building blocks from which the science emerges. So if we look at where we are today, it bears a lot of resemblance to what the world of physics looked like 100 years ago. In the late 19th century, there had been tremendous discoveries, superconductivity, radioactivity, the discovery of the electron, and so on. And there was a belief, a nagging suspicion that buried in there is order, some kind of order, but was not totally clear to us what that order was. We didn't even really understand the difference between atomic number and atomic weight. However, we developed a solution as a community, as the physics community, that reduced this complexity. It made it so simple that we learn it in high school today. And of course, this is the periodic table. There's a big picture of it on every physics lab. It looks like this. If you were to try and encode this in JSON or XML, it would take a few kilobytes. In those few kilobytes, there's a tremendous amount of knowledge and learning that is encoded. And so the question I'd like to pose to you to think about is, for our field, for edge computing, cloud computing, IoT, cyber-human systems, cyber-physical systems, is there a way to distill these systems down to their core basics in a way that gives us simplicity? And by doing that, we bring a little bit of order to the conversation. I want to emphasize, it took 30 or 40 or 50 years for the periodic table to evolve to take the form that we have today. So what I'm presenting to you today is only the beginning of a conversation that is likely to keep going for quite a few years and likely evolve over time. So here's a one-slide summary of my message for you. It appears that thinking about the computing world in terms of tiers gives a lot of simplicity. And it's simplicity that has all the right attributes, just as I was mentioning a moment ago. Now, any given tier can be implemented by different people. So for example, the cloud, we have AWS, we have Azure, we have Google Cloud, we have many others. But by virtue of being a cloud, automatically with it comes a whole host of constraints and opportunities. Similarly, if you are a mobile device or an IoT device, there's a different set of specific challenges and opportunities that come with it. And so what I'm trying to do is to paint a picture of the world in a way that focuses on these inherent attributes at different tiers, rather than the specific solutions that a given vendor may have come up with. In this picture, if you look back over the past 50 years and look forward over the next many decades, the introduction, repurposing, or disappearance of a tier maps to what we think of as a major shift in computing. So the addition of edge computing is one of these. The emergence of cloud computing is one of those. The emergence of time sharing many decades ago is another one of these. And so let's look at these. Also, in terms of time frame, it appears, just empirically looking at history, that a given structure appears to be stable for about a decade. And roughly by the end of the decade, the accumulated innovations and changes result in some change to the fundamental structure so that a new tier appears, a tier disappears, or there's some repurposing, there's some change to the system. I also want to contrast this tiered model to something very familiar to many of you, which is the hourglass model that is used to describe the world, for example, of the internet, where you have today's web services like Zoom, on which this event is being broadcast, and the underlying networking technology from Cisco or Juniper or various wireless technologies of various kinds. And the glue that holds them together are this very small set of internet protocols, IP, TCP, and so on. This is useful, and the tiered model is different from the hourglass model. They both have their purposes. A very important requirement is that in the tiered model, there is no expectation that if you take tier one from vendor one, say from Google, and you try to add tier two from a different entity like Microsoft, the two should interoperate. There's no expectation of interoperation. A given vendor usually creates elements that are present at all tiers. But if you look at the offerings of different vendors, you will see that they're solving at each tier the same set of problems. The solutions bear a lot of resemblance, and is a very useful way to tease apart incidental complexity from inherent complexity. So, what is this tiered world? Until recently, the world consisted of two tiers. I would say until the mid-2015 timeframe or so. You had the cloud on the right, which was tier one in this picture. And then you had things like desktops, laptops, smartphones, things of this kind, which were the way in which you used the cloud services. The picture today, the world that is emerging now, has four tiers. You have the cloud, which is unchanged. You have the world of desktops, laptops, but it's now much richer. You have here IoT devices, such as video cameras, drones, wearable devices like HoloLens from Microsoft and other devices. And you have this intermediate tier, which is the edge computing tier. And as Saeed pointed out in his talk, there's fine structure here, which I'm glossing over and collapsing all of his multiple layers into a single term called cloudlets, referring to any one of those intermediate tiers. So the critical requirement of the edge in this picture is that it have network proximity to tier three, okay? So let's look at what each of these tiers gives us. The cloud offers you compute elasticity. You basically ask for more compute and you get it on demand. You may have to pay for it, but it's basically an infinite source of computing. That's the abstraction. It's also the safest place to keep your data. If you want to archive data that you can retrieve 100 years from now, you put it in the cloud. And last but not least, the cloud represents extreme consolidation. The economies of scale are exploited to their maximum in the cloud. There's no other place anywhere in the system that offers computing so cheaply. So the lowest cost per compute is in the cloud. So if these three attributes are key, and none of the other attributes that I'm going to talk about are important, there's no better place to do your compute than the cloud. Tier three which is the mobile and IoT tier, is where all the action is. This is where humans live. If you have to interact with humans, you have to be at tier 3. This is where data is obtained. Video cameras, drones, all of the other stuff that interacts in the real world is at this tier. So mobility and sensing and actuation all happen at tier 3. Now, the reason edge computing is needed is because to get the full value of tier 3, you need the compute capabilities comparable to tier 1, but you need it at much, much lower latency and much, much better scalability. And so the purpose of tier 2 is to provide cloud-like capabilities much, much closer. So Saeed, in his introduction, pointed out that it is bringing the cloud closer to the IoT devices. And that's exactly the reason why we chose the name Cloudlet, to indicate a small cloud close by that performs this job. Now, people often ask me the question, how close is close enough? The only answer I can give you is to paraphrase what Albert Einstein once answered in response to the question, how simple should a theory be? And his answer was as simple as possible, but no simpler. So in that vein, the answer to the question, where should the tier 2 be located? How close is close enough? You should place it as close to the cloud as possible, but no closer. In other words, the economies of scale, the simplicity of management, all of these argue that as you go further to the right in this picture, you drive down management cost. As you move to the left, management cost increases. And so the reason to use edge computing is to strike a balance between management cost or administrative cost and the performance attributes that you can get, but by being close by. So at the speed of light, fiber transmits 200 kilometers in 1 millisecond. So all of the state of Pennsylvania, or at least half of it, could be covered by a single cloudlet. So city scale cloudlets or county scale cloudlets are entirely possible. And in fact, we are already starting to see some of this emerging. If your networking is not quite at that level, if it introduces more latency, you may have to bring the cloudlet much closer. So the demands of the application and the demands of the network are the key drivers of physical placement of cloudlets. Now, in this picture, I also have on the extreme left tier 4. Not going to say much more about them in this other than this slide, but these are elements that have no chemical batteries. They harvest energy, use it briefly, and then go back to being passive. So the best example of this are RFID tags, but there are many other devices of this kind emerging, and they harvest energy from tier 3, awaken briefly, perform computation and sensing, and go back to sleep. So physical proximity, not just network proximity, is needed to do the harvesting of the energy. So this is the picture, the world in question. Now, how can you make use of thinking about this picture? First, as I mentioned to you, you can use this to think about competing offerings from different vendors. If you're looking at Microsoft stack and you're looking at Google stack, and you're asking, how do they map to each other? A good way to ask is, what are their tier 1 components? What are their tier 2 components, and so on? Second, if you inspect a system and you're trying to understand, does this have to be so complicated? Why is it this way? The answer to that question is also helped by thinking about which parts of this are at which tier. And is it the case that by moving this functionality to a different tier, you could in fact simplify the system? Does it really need to be here? if you're designing a new system, you can use this mental map to place functionality. You can challenge assumptions in the systems and ask, in 2023, does this functionality really have to be at tier 3? Could we move it to tier 1? If we can't move it to tier 1, could we move it to tier 2? What would it do to the per unit cost of a tier 3 device? Or what would it do to the battery life of tier 3 device? So in many ways, identifying missing functionality, suggesting new functions, exposing hidden assumptions, we have found this tiered model of computing very valuable. One thing that comes out as you think about this tiered model is the central role of energy in the whole picture. So if you look at the extreme right, tier 1, those data centers consume megawatts of power. In fact, the placement of some of them is chosen to be close to things like hydroelectric dams so that they can leverage the cheap energy that is located there. So energy is a very big consideration. And of course, cooling and power delivery and all these kinds of details are a big deal in data center management. At the extreme left, at tier 4, you are obsessed with energy. Every joule that you can harvest is valuable because you have no energy supply of your own. At tier 3, mobile devices, on smartphones, on wearable devices, on smartwatches, on things like Google Glass and HoloLens, battery life is a big deal. Designing the systems to be able to operate so that they can last many hours is crucial. So the only tier at which perhaps energy is not dominant is in fact the personal computing world, the desktop, the laptop. In 2023, it's perhaps a solved problem mostly, how to do energy adequately for laptops and certainly for desktops. And so cloudlets, to the extent you can map them into tier 2, have this huge advantage that because they're neither at neither extreme, standard cooling mechanisms such as convection cooling in human habitable spaces works out to be adequate. So I want to use this tiered model to help you understand how our world has evolved. In the beginning, and by in the beginning, I'm talking here early 1960s, only tier 1 existed. Machines were big. They filled an entire room, like this big classroom that I'm teaching in. And these were the mainframes. Now, you had no networking. This was 1960s, but it was possible to use a very limited form of communication, point-to-point links. And it was amazing what was possible using that. So a lot of the telemetry, early days of remote sensing telemetry were done using this method. The invention of time sharing can be viewed as improving elasticity. So remember the EC2, the E in EC2 stands for elastic cloud computing. The fact that the cloud seems to expand or shrink on demand is its unique property. And time sharing gave you that property in the world of mainframes. You had 5 new users, they could log in, they could use the system, as long as the statistical multiplexing of resource demands by each user was modest, and as long as you were below the saturation level, things worked beautifully. Of course, life was not always so simple. As you approached the bottleneck limits of compute, the queuing delays experienced by individual users grew unacceptably long. And so the solution was to introduce tier 2. So the critical innovation of Butler Lamson and Chuck Thacker was to say, look, computing, this is 1970, computing has become cheap enough, chips have become cheap enough that we can give each person their own. Why share? Why pay the penalty of queuing delays? So the whole world of personal computing, which replaced mainframes and time sharing, arose out of this. So tier one vanished, and you had this disaggregated world of tier two entities by the mid 1980s. Unfortunately, during the 15 or so years of time sharing, companies had evolved workflows that used time sharing in a very important way that was hurt by the move to tier two. They had used the shared information systems, the file systems, in order to do sharing, controlled sharing of information across users. So the manager of a project could give access to all files to a particular group of users. He could allow permission to do reading, but not writing, and so on. All of the things that we take for granted today about sharing, controlled sharing, all of those emerged in the context of time sharing. The problem was, once you move to a disaggregated world of tier two devices, this was no longer possible. So the ENDRA project here at Carnegie Mellon, which was jointly created by IBM and Carnegie Mellon, created the ENDRA file system, whose goal was precisely to solve this problem, to give you tier two compute capability, but to give you all of the benefits of tier one from a time sharing viewpoint for information sharing. And so this, although it was back in the 1980s, so the word cloud had not been invented yet, this was one of the earliest examples of cloud storage and sharing at fine grain using the cloud. So today's Dropbox mechanisms and many Box, Dropbox, and other distributed file systems follow from this early work. By the early 90s, people had figured out how to make these desktop machines much smaller, much lighter. So as far as I know, 1987, the compact luggable was the earliest mobile device. The Radio Shack TRS-80, which was used by quite a few reporters, had a 300 bits per second, not megabits, not kilobits, bits, 300 bits per second modem, but it was good enough for reporters to use in the early 80s. And so within a decade, we had created the form factor that we think of as a smartphone today. By the end of the decade, in the start of 2000, we had already the smartwatch. And the iPhone emerged in 2007, and wearable devices, commercial products by the mid 2010 decade. On communication, again, here at Carnegie Mellon, we pioneered the world's first wireless communication environment at 915 megahertz deployed on campus. This was pre-IEEE 802.11. But the lessons we used to define the 802.11 standard. PC cards emerged before 2000. Centrino, which is an integrated chipset by the early 2000s by Intel. And of course, today we have 3G, 4G, and 5G being widespread. One of the important consequences of mobile devices is something that I call the mobility penalty. And this is unique to tier 3. So I have here on this slide, if you notice, it's an article from 1993. So that's exactly 30 years ago. Now, I was 30 years younger and much bolder. And so if you read the text here, it's a pretty bold claim. It says mobile elements are resource poor relative to static elements, regardless of future technological advances. A mobile unit's weight, power, size, and ergonomics will render it less capable than its static counterparts. While mobile elements will undoubtedly improve, they will always be at a relative disadvantage. I would never say something so bold today, but fortunately, 30 years ago, I was much rasher and I was willing to say it. The good news is that 30 years later, it is still true. This table shows you from 1997 to 2020, the relative compute power of a wearable device in blue, a mobile device like a smartphone in red, and a typical server of that era in green. And you can see that gap, which I refer to as the mobility penalty, by just the virtue of having to be light enough, small enough, have long enough battery life, that exacts a significant penalty on what you can do computationally. So we have learned a few things in 30 years, that it's not just raw power that matters, but it's performance per watt. That if you can specialize the functionality, that it's a huge win. But these alone cannot close the gap. What you need to do is to leverage resources in the infrastructure to overcome the mobility penalty. So this this figure from 1997 shows the world's first speech recognition on a mobile device, done here at Carnegie Mellon, leveraging offloading. The term that we use today is called offloading from a mobile device to the infrastructure. And this basically led to offloading becoming a widely used technology today. The only complication is, where exactly do you offload? And the emergence of the iPhone in 2007 suggested that the example of Siri, which is speech recognition on the Apple iPhone, suggested that all you needed was tier 3, the mobile device, and tier 1, the cloud. Unfortunately, latency does matter. I believe I only have 2 minutes left, so I will skip these slides on latency. And so the way you overcome latency is by leveraging this new tier of computing, tier 2 edge computing, so that you are able to obtain the offloading benefits without paying the price in performance. So this turns out to be a big use and driver of edge computing. So where we are today, before I end, is we are on the verge of an explosion of edge native applications. Notice I did not say cloud native, it's edge native. Edge native applications cannot run in the cloud entirely. They cannot run on a device entirely. They depend uniquely on one or more edge attributes. So it's useful to say what these edge attributes are. One of them is what Saeed referred to, bandwidth scalability. If you have IoT devices like video cameras producing megabits per second, pushing the processing close to them makes total sense. It's the only way to have a scalable network. If you close the loop and you have to have real-time drone control or augmented reality, a cyber-human system, then in addition to bandwidth scalability, you need low end-to-end latency. If the data in question is sensitive, if I put a video camera pointing at my backyard and I don't want it to have pictures of my children sent to the cloud, the ability to strip selectively privacy sensitive information is another capability that edge computing can do for you. In some use cases and some parts of the world, connectivity to the cloud is flaky at best. The ability to have fallback services provided by edge computing is valuable. And last but not least, there are legal reasons. For example, in Europe, the a GPR, General Data Protection, GDPR regulations say that you cannot export certain kinds of data out of the country. So edge computing provides you the platform to ensure the data sovereignty that you need to meet in these cases. So if at least one of these is essential in your application, then you have an edge native application. If none of these is needed, you don't need edge computing. It's an expensive luxury. Use the cloud and it'll do fine. So in closing, I hope this picture that I've painted for you of a way to think about our emerging world as being really simple at its heart. It's a tiered architecture. It is driven by the fundamentals of space, time, and most importantly, energy, and it's going to evolve in the future as it has evolved in the past. Thank you.